Hey, what's up guys? My name is Cherno. Welcome back to my game engine series. So last time we took a look at renderer API abstraction. Check out that video if you haven't already. We basically just pulled out a bunch of our code into specific classes that were kind of per render API. So we're dealing with OpenGL at the moment. So we created like an OpenGL Vertex buffer and index buffer class that was specifically for dealing with those kind of render API like primitives or just things essentially in a way that was kind of abstracted out where when we kind of call it from our application or from our game kind of code or from our renderer code, it doesn't care which API is actually used under the hood. So definitely check out that video if you haven't already. We're going to kind of continue down that slope today, but we're specifically going to talk about buffer layouts. And when I say buffer layouts, I mean, I'm really talking about Vertex buffer layouts, okay? We touched on this, we've touched on this on my channel just in general because of course you can't really render anything without having to deal with Vertex buffer layouts. I think I have a video specifically about that in the OpenGL story, so I'll try and link it up there. Definitely check that out if you haven't already. And in general, if you're not familiar with the OpenGL series, I would just take a look at pretty much all of it because that's really going to help you out with what we're kind of building here at this moment in Hazel. And also, I'm gonna continue that OpenGL series probably next week, probably throughout this kind of next week, because it's going to be really important in kind of taking a deeper look at some of these concepts that we're learning here in the Game Engine series. So anyway. Today, we're going to talk about buffer layouts. So what does that mean? Why do we need them? What do they do? And how do we write them in a way that is both abstract and works for every render API, but also is actually kind of easy for us to use because that's kind of what I'm all about, right? I want the code that we write on the client side, the code that we actually write like inside our game kind of project, right? Or inside our renderer to just be beautiful. That's kind of what I go for. That's what I aim for, right? And it's actually getting dark outside because I left this video pretty late today. I was just planning it and just making sure that I had everything that I wanted to say figured out because I really want to do this well. This specific episode, well, all videos really, come on, but you know this specific episode. So if it kind of gets darker, I'm sorry because it is like the sun's about to set in half an hour. Anyway, the point is. Beautiful code, right? I think that's really important. I think that if the code that you're writing, if you design an API and the code that you're writing just looks disgusting or just is hard to do things with or isn't concise enough, that's an issue, right? Think about writing documentation or just writing like an English essay or something like that, right? If you take paragraphs and paragraphs to kind of describe the same thing and you just can't make really like nice kind of flowing sentences, that doesn't really sound nice. It's not good for the reader to read. And just apart from that, not just like, it's just not nice. Aside from that, it's just not like actually practical. It just doesn't work as well, right? Like the person might have to read your sentence multiple times, or they might have to read a whole much more information that they otherwise would have to understand what it is you're trying to say in your English essay, right? And of course, English essays, you're probably going for a high word count anyway, so you might just reiterate stuff over and over again. But in code, that's really not the case usually. Like you actually are trying to be concise, right? And just in general, you want to use kind of grammar and sentences that both kind of sound nice, kind of in your essays, right? In your English essays, back to this. But also stuff that actually gets your point across very just concisely and just nicely so that the person kind of wants to keep reading and so that the person forms a good visual kind of mental image of what it is you're trying to do. And everything is just beautiful and everything just feels solid. That's what we want to achieve with all of the APIs in this engine, right? That is what we want to do. That's not easy to do, right? But because we're using a language like C++, it's extremely flexible. And it actually means that we can do a lot of what we're trying to do. And today, specifically with buffer layouts, I'm going to show you how there's many different ways of essentially doing the same thing. But I want to do it in a way that actually looks good. Like we're talking about a buffer layout. We should just be able to visualize the code and be like, I get everything, right? I get everything. Like we don't want some weird, weird kind of way of writing code for this buffer layout where it just doesn't make sense or it just requires us to really think about what it is we're defining. No, we want it just to be easy. We want it to just be really easy because if it is easy and if it is just so nice, right, and elegant, then apart from just looking good and us feeling good about ourselves and also other people dealing with this and being like, this is great, this is so easy, apart from that, it's also actually going to reduce the bugs in our code. Why? Because everything just makes sense. And if something is wrong, we can intuitively kind of just pick up on that. We don't need to just read the documentation and be like, yeah, I guess that's wrong. No, we can just see the errors right there because it's laid out in such a way where errors are obvious, okay? That's what we're going to talk about today. We're going to jump in and we're going to take a look at just the practical example of what we actually have, as well as talk about what it is we're trying to kind of create. And I think that that's really important when you kind of talk about any kind of API that you want to design or any kind of complex concept. It's what is this actually doing, right? And with Vertex buffer layout specifically, it's very simple. You know, what we're doing is we're actually telling OpenGL this byte array of data, what's in it? How is it broken down? You know, how many elements are there? How many, like, what are the elements? You know, is this a 3-component vector of floats, right? Or is it just 3 separate floats? You know, is this a 4 kind of component color? How is it specified? Is it just, maybe it's just an unsigned integer, you know, or maybe it's 4 separate floats or something like that, right? It could be just absolutely anything. Like if it's just a binary blob of data, which is what our Vertex buffer actually takes in and uploads into the GPU, we need some way to actually describe the layout of that data, which again means, you know, the first 4 bytes might be a float, the second 4 bytes might be another float, and then the third 4 bytes might be another float. That's 3 floats in a row. That's our 3-component vector that describes our vertex position. Stuff like that. That's what we're trying to achieve. Let's try and do it in an elegant way. Let's jump in, take a look at a practical example, and we'll see how we go. Okay, so last time I had this triangle. Today we're going to basically aim to achieve the same thing, but a lot more elegantly. And specifically, we're also going to maybe jam in some other vertex attributes for fun, just to kind of see how they work. Maybe we'll just throw in a vertex color or something like that. Let's just close this. So currently we are actually specifying a buffer layout, right? If we weren't, we wouldn't see anything on the screen. And that's this right here. Okay, these 2 lines of code. What this is saying is inside our vertex buffer, this one that we're creating, we have at index 0, 3 floats, right? They're not normalized. The stride between each vertex is that size, so 3 floats, 12 bytes, and the offset of this particular element is nothing, right? Now, I don't really want to discuss how this works too much because I do have an OpenGL video about it, and as I said, the sun is setting and I have like other stuff to do with my life and I don't want to sit here for 2 hours just reiterating, wasting your time, just describing everything that I already have already. So definitely check out that video. That I don't know, like this is like, in my opinion, quite simple to understand. So if you don't understand this particular line of code, make sure you check out that video because I'm not going to really talk about it too much, I think, in this episode. So a few things that I actually want to point out with this particular line of code is, I guess, the linkages of it. So what it's referring to, what it's linked to, what it corresponds to, right? So vertex attributes specifically are actually stored in the vertex array, not the vertex buffer. Now they describe data in a vertex buffer. However, a vertex array is kind of the parent type, if you will. And a vertex array can contain multiple buffers, right? We can actually interleave our buffers and have, you know, just in this one vertice, like, right, in this one kind of vertices array, we could just add, you know, we want a vertex color or a vertex normal or something. We can actually just add it like just bam, like that, you know, and that way, you know, every single vertex that we have is kind of going to contain, in this case, maybe both a position and a normal, right? Or the other thing we could do is kind of just not interleave it, so not have any of this, right? But then just make another kind of array here, right? Another float array, which has had vertex normals. And then we can actually upload that into a separate vertex buffer. We can create another vertex buffer just for the normals, and then another one for the colors, and then another one for, you get the point, right? So because of that, OpenGL doesn't really care how you do that. You can interleave all your data and have one big fat vertex buffer, which is pretty much what you want, like 99% of the case, by the way. Or you can split up your vertex buffers into separate kind of actual vertex buffers and separate buffers of memory and then upload them individually. It doesn't matter because this stays the same, right? It's just you happen to bind different vertex buffers at certain times when you actually describe your vertex array. And we'll kind of maybe talk about that in the next episode, because next episode we're going to talk about vertex arrays and actually abstracting them out into a class, which means this kind of stuff. But anyway, what I want you to know is that this particular binding, this kind of, I'm enabling a vertex attrib array and specifying the layout of my buffer, that is stored in a vertex array. If I bind another vertex buffer or something, like if I don't need to redefine this, all I need to do is this state gets saved into my vertex array. If I want to recall it for rendering, I just simply bind my vertex array again and it's done, okay? The second piece of information is that this is directly tied to our shader, right? If we look at a shader, like we've specified one here, look at this, layout location equals 0, vec3, a position, right? That's this piece of data. 3 component vector, right? 3 floats, that's what a vec3 is, right? Not normalized. 3 times the size of floats, so 12 bytes, again, the size of this type. Index 0, layout equals 0, rather location equals 0, right? That is what that's tied in with. If we suddenly want to take in a normal, right, we put that in location 1. Let's just go with the color in this case because it's a different type. A vec4, and this will be our kind of vertex color, right? What do? We duplicate this, right? We have it at index 1, and by the way, we also need to enable it. So enabling index 1, we have 4 floats, and then the rest is kind of the same, except this changes. Because that is, oh, and this is wrong, by the way, sorry. This isn't the size of, this is the stride. So it's actually the size of each vertex, not the size of each element, right? So it's kind of the size between each vertex in the array. So if we have 3 vertices, it's the size of each full vertex, which would be the size of both the position and the color in this case, which would actually be 7 times size of float, and that would be the same for both of them. So this changes to this, right? And then the offset is the offset of this particular element, right, inside the buffer. So obviously this is a vec3, that's 12 bytes, 3 floats, right? 12 bytes. So the offset of this is going to be 12. So it's simply 12, right? And we just need to cast it to a const void pointer. Okay? Const. Okay? So that's kind of what we end up with. But you can see that it's directly tied to my shader. That's the kind of the point that I want to drive home right here, is it's tied to my shader, okay? And it's actually not really tied to shaders in OpenGL in the sense that there's no validation performed between that. In DirectX, it is absolutely performed, right? You cannot describe a vertex buffer until you've bound a shader, okay? So it's actually a bit different than how OpenGL works. Anyway, that's kind of my point. So because it's so heavily tied with my shader, what I actually want to kind of do for my buffer layout is I basically just want to be able to set a buffer layout onto a vertex buffer, right? Now I did just say that they're tied to vertex arrays. However, a layout describes a vertex, like a layout is specific to a vertex buffer. It describes the layout of an actual buffer of memory. So whilst OpenGL kind of stores this state in vertex array, in DirectX, they're specifically on vertex buffers because there's no such thing as a vertex array in DirectX. But apart from that, it just makes more sense to us. So to us, it doesn't really matter that they're actually stored inside vertex arrays because we can still kind of work around that and store them wherever we like. It's just that in the end, under the hood, we'll make that differentiation when we need to. But the kind of surface level API should still set it onto the vertex buffer. Now, how do I describe this layout? Well, there's a lot of ways that you could do it, but I'm not going to waste your time and show you all the bad ways of doing it. I'll just show you a nice way of doing it, which is, again, what I'm talking about, where we want to kind of have an elegant visual representation of this. Wouldn't it be cool if, when we kind of describe this layout, we could somehow literally just have this kind of code, like right here, and just be like, you know, our layout equals kind of, maybe put this in brackets. Our layout equals like that, right? Now I just realized I've got white spaces on, which we don't need. Wouldn't it be nice if we could just do something like that? Well, that's kind of what we're gonna do. We're gonna actually literally make it so that we can see a visual representation of our layout. So our goal is to have something that's maybe called a buffer layout class, right? Which is gonna look like this. And then maybe what we'll have is each element is going to be kind of defined like this, okay? And we're going to achieve this by just using an initialize list and probably storing these elements in a vector. Now we're not going to use vec3 or vec4. Those are GLM types in this case. Well, in here they're obviously they're GLSL types inside the OpenGL shading language. But what we're actually going to do is come up with some kind of enum that describes this data type. So we're essentially going to probably create like an enum class called like shader data type, which will be kind of our cross API cross-platform way of just kind of defining each data type that is inside a shader. So like vec3, vec4, you know, float, int, that kind of stuff. So we'll probably use something called like float3 to describe a 3-component thing. You know, vec3 is cool and all, but I kind of like float3. That's kind of the HLSL style way of doing things, and we are probably going to eventually switch to HLSL shaders. You can use vec3 if you want, because that's kind of tied to our math library in like at the moment. But I'm just going to use float3 to describe a 3-component float, right? Because it makes sense. And then we'll probably give it a name. Now you don't really need to give it a name. It's useful to give it a name. Like in DirectX, we will have to supply some kind of string, as you'll find out in the future, but it's just nice to kind of give it a name just so that you know what this actually is. And if you want, you can actually call it the same thing, which is what I'm kind of doing in this case. So we might have that. Let's just get rid of this whole color thing. I mean, essentially you do the same thing for color though. You just make a vec, like a float4 and do all of that, and that's gonna look really nice, right? We'll get rid of color here. And we'll get rid of this stuff, change this back to 3 floats, and we'll try and just render that triangle to begin with. Okay, so this is my layout, and then I'll set my layout, and that's kind of it. That's actually how I want to define my layout. And you can see that it becomes really nice, because suddenly if I have a layout that's full of like stuff that I need, you know, like, you know, we might have like texture coordinates or something, and you know, you have something like text coord and maybe normals, and then you might have like a color or anything. It's just so easy to see the layout of this buffer, right? It's amazing. That's all I need to do. And obviously if I want to like have an array of things, or like, you know, if I want it to be normalized or not, I can maybe add a third parameter, but this is kind of what we're going for. So let's take a look at the magic to make this happen. So I'm going to define all of this code inside the buffer file here, because it is to do with buffer layouts and all of that stuff. So I'm going to make a class called buffer layout. Okay, and a buffer layout is essentially going to contain a vector of buffer elements. Okay, and these are going to be called elements. I'm immediately just going to give it a getter to return that, because we are going to need that. So get elements const, and that will return elements. Okay. And then these buffer elements are going to be another class. Actually, I'll call this a struct, buffer element. And this is going to contain all of the stuff that we need to actually specify. Okay, so the first thing it will contain is a name. So std string name. I mean, in no particular order, we need the offset, we need the size, we need what else do we need? The count, I guess, because we can have like multiple of these. I'm not really sure if we need that, to be honest, because I'm just thinking about it. Like, we definitely need that for uniforms if we have like an array, but we don't generally. I think if we just have that shaded data type, as I said, which is going to be the type of data, we'll kind of know the count of how many elements we have anyway. And we can always create helper functions to kind of convert between the two, right? So we'll maybe have the name, the type, the size, and then the offset. And I think that should be enough, right? Now, the way that we constructed this over here was just by writing the type first, right? And then the actual name. So we can actually do that here as well. We just need to create a constructor that allows that kind of construction, right? So I'll write const std string name, and then shader data type. All right, and then over here, we will set everything. So name will set to name. The type we will set to type. Size will set to 0 to be, size we can calculate pretty much immediately, I think, because that's just the size of the type. So we probably don't need to set that, although we can here as a default. And then offset will set to 0. Offset we can really only calculate once we have context. So offset is going to be the offset of this element inside our layout. So obviously, to calculate the offset, we need to be aware of all of the elements in there. Because if this is like the second element, its offset is going to be the size of the first element, right? Because that's how much into the buffer it is. So we can't really calculate that just yet. But we can calculate the size, so we might do that. Anyway, enum class shader data type. Right, and we can make this like I mean, if you wanted to, you could make this like a UN8T or something just tiny because it doesn't really need to be very big. I don't really, it doesn't really matter, you know. I'm not one to just, like, this isn't going to be serialized. This is not, like, maybe if it comes down to us trying to really pack this data in tightly, we can do that in the future, but you don't need to in the, like, for the time being. So we'll have none, we'll have float 2, we'll have float 3, we'll have float 4, we'll have, I guess we can do, like, mat 3, mat 4, this is not just going to describe attributes, by the way, it's going to describe everything. We'll have int 2, int 3, int 4. Yeah, that's probably good enough. We might have like struct or something for like uniforms. We'll cross that bridge when we get there. Okay, that looks pretty good to me. That's a good like basic type. You can have booleans as well. Maybe I'll just write bool at the end here. Okay, that's pretty good, right? So that describes all of our types. Now, two things I'm concerned about is the size and also the offset, which we can calculate in a minute. So what we can do is create some kind of function, obviously, that converts between this kind of shaded data type and an actual size. So what we can do is just create a static uint32t shaded data, we can just do shaded data type size, I guess. Shaded data type size, shaded data type, and then this will simply, my letter E seems a bit jammed because I can't type it without pressing hard. This is just going to be a switch, see? This is just going to be a switch statement that goes between, that basically just switches on every single type that we have. So shaded data type, we'll begin with float. And in this case, it just kind of, I don't know how, let's just go 1, 2, 3, 4 for now. This just returns the size of it. So a float is 4 bytes, so it's going to return that much. And we'll also kind of do the same for pretty much everything else. So a float 2, 3, 4, mat 3, mat 4. I'm going to try and be comprehensive. Usually I like adding these things as I go just because this just takes a bunch of time and makes the video more complicated, but I'll do it at least for this for now because it shouldn't take too much time. All right, I think that's it. So all of these, right? I can just align these a bit. Okay. So float 2 is going to be 4 times 2. Float 3 is going to be times 3 times 4, right? A mat 3 is going to be times 3 times 3, right? Because it's a 3 by 3 matrix. A float 4 is going to be the same, but 4 by 4 matrix. An int's going to be 4, an int is going to be, an int 2 is going to be that. You guys kind of get the point. And then a bool's probably, I'm not sure, it might be 1 byte, it might be 4. We'll see about that, but we'll just leave it as 1 for now. And obviously we'll return 0 if we have nothing. And also we should definitely assert here. Core assert, false, unknown shader, unknown shader data type. Okay, and we don't need to print out the type because that'll just break here and we can just inspect it using the debugger ourselves. Okay, there we go. That's everything. Hopefully I didn't make any mistakes. I was kind of hasteful here. But now we can actually see what the type of each piece of data is. Right now this is in buffer. Remember, when we actually move this into shaders and have more stuff, we'll deal with that kind of then. Okay, cool, right? So what we want to do now is actually calculate that size, right? So right here in size, we can already just call shader data type size and then pass in the type. All right, and then we have that. Beautiful. Now, and this is just buffer element, of course, not buffer elements. When we create a buffer layout, right, what we want to be able to do is take in and initialize a list, right? So this kind of thing. Now, this is interesting because ultimately you could just say, I just want to take in like a const vector, right? Because if you take in a vector, and it doesn't matter if it's const reference or whatever, that letter E is annoying me. It doesn't matter if it's const reference or whatever, but if you take that in, like this kind of should work. It doesn't because there's 2 implicit casts happening, but just so that if we just take this type, technically speaking, and we change that and make it this type, right, that will actually work, right? So you can actually construct something like this. Now, It's not working this, yeah, we've kind of put this the wrong way around. I don't know how I did that so easily as well. So we put the type first and then the name in the actual list here. So if we get rid of this and go back, it should work. Yeah, there we go. See? And then what you can do is actually decide that I want to make a layout from my layout, right? Can't really call this layout, but whatever, you get the point, right? But unfortunately, I can't just do this. Okay, because there's one implicit cast to convert a vector, like an initializer list into a vector, and another implicit cast to convert the vector into a buffer layout, because buffer layout has a constructor that takes in vector. So we can't actually do that. What we can do, however, is actually just take in an initializer list here, right? And then if we actually do that, right, then, and you know, you can do like your const reference here. If we do that, you can see this works. Okay, beautiful. So now we basically got exactly what we wanted, which is pretty cool. And then from this, right, how do we convert it into a vector? Well, as I said, there's obviously a constructor for vector that takes in an initialized list. So we literally just do, I guess I'll do maybe layout or elements, we'll call it, just like that. Okay, there we go. So now we can construct one of these from here, and all of the data that we've actually set is inside this vector, which is very cool. Now, once we have that vector, we actually need to calculate the offsets. So I'll say calculate offsets, and there's one more piece of information that we need, and that is the stride. And the stride is the size of each vertex, each complete vertex. So all of the attributes, the size of all of those together. That's only known after we have the whole list. Same as the offset, right? So we can calculate that once we have the whole list. We can't do that inside buffer element, but we can do that here. So I'll make a uint32t called mstride, which we'll set to 0 by default. Calculate offsets and stride will be a beautiful function that we have here. That's going to be private. So void calculate offsets and stride. That's going to go through all of the list, all of the elements that we have here. So I guess we'll just say for auto reference elements in this letter E is really annoying me. In elements, right? And what we're going to do is we're going to maintain an offset here. And then I guess we can set mstride equal to 0 here, just in case we recalculate it or something. This is what we're going to do. We're just going to say that the element offset, right, is going to be our offset. Then we're going to say offset plus equals element dot size, right? And then we're also going to say mstride plus equals element size. Okay, so that should set all of the offsets and all of the and also calculate the stride for our entire buffer layout. I think that's about it, to be honest. What haven't we done? I think everything's, well, I don't know. We should just check it out and see if it works. So, we haven't done vertex buffer set layout. We'll do that in a second. I'm just going to put a breakpoint here, launch this, and see if that layout is everything that we want it to be, and more, potentially. I should probably add something else into the layout, because just, you know, I mean, this is going to be pretty boring, I think, if we just have one thing in there. But if we take a look, so our layout has one element, a stride of 12, which is correct. And the position has an offset of 0, size of 12. Okay, looks good. Let's just to test it a bit more. I'm going to add 2 more things. I'm going to add a another float 3 and then a float 4. Maybe I'll put the float 4 in the middle just to make it a bit different. So we'll pretend that we have normal in the color. We'll see what that looks like. Okay, okay, I was going to say it didn't compile, but that's because we put the comma in the wrong place. Let's just try again here. Okay, so layout. The stride is 40, is that correct? So 16 plus 12 plus 12. Yep, that's correct. It's 24 plus 16. Size is 3, and these should have correct offsets. Offset of 12 and offset of 28. Beautiful. Okay, so there we go. Our layout clearly works, and that is really cool. So now let's try and render something with it. What I want to do is go into our buffer class, right, to our buffer file, and just add, you know, a virtual void set layout, right? Buffer layout, We'll take that in as a const reference. Layout equals 0. And then we'll also have a virtual const buffer layout get layout. So I want to be able to get and set the layout, right? We'll open up GL vertex buffer, or rather GL buffer. And inside here, these should all be overrides, by the way. Not sure why they're not, because I was lazy, I guess. So now we're going to have const override for all of these. And these two, well, get layout. So we're going to store the layout here. So we'll have buffer layout, m layout, layout. Get layout is just going to return it. And thank you, Visual Studio, for that horrendous formatting. And then this is just going to set it, right? So m layout equals layout. We'll make both of these. Yeah, that's fine. Okay, done. So there we go. I was going to make them inline, but there's no point. That is done. Now we should be able to just rock and roll with this. Now, as I mentioned, this particular code it gets set in the vertex array. We'll talk about that next video because we haven't abstracted that just yet. So for now, we'll just do that stuff here. And you'll kind of see how it works. But in the next episode, we'll move it into the appropriate location. I could end the episode here, but I'm not going to, just because I actually want to see this stuff in action and rendering. And I did promise you guys vertex colors. Okay, so to make this stuff work, what I need to do is iterate through every element in the layout. Now I could write code such as, for const auto element inside layout.getElements, but I don't want to. I just want to write code like this because it just looks better. So in buffer layout, what I'm going to do to make that happen is the same thing that we did inside layer, if you remember, which is where I actually, inside layer stack, where I actually provided iterators, begin and end. So if we copy this code and then go into buffer, inside buffer layout, get elements, I can just provide an iterator here. Obviously in this case, it's going to be a buffer element instead of a layer. And then this is just going to be m elements, begin and end, and there we go. Okay, so now we can just do that, which just looks nice. So we're iterating through every element in the layout, and we just want to do this kind of stuff here. So we'll keep track of which index we're up to. All right, could have just used a regular for loop just that has that built in, but this is also fine. We'll set the index here, and then we'll increment the index. Now this is where it gets interesting, okay? So what we need for OpenGL is, we can't just say that it's a vec3. We have to say that it's actually 3 floats. We have to say the type and then the count, as if it's like not one variable. Now in DirectX, you don't do that. You just say, this is a 4-component vector, or this is a 3-component vector, or a 2-component vector. So that's why that's why I haven't written this in a way that is just like, type and count, as if we have type being float and then count being 3. That's weird. I don't like doing it that way. And DirectX doesn't want it that way anyway. So what we need here is some kind of conversion to take place. So it'd be nice if just regardless, elements just had a component count, right? Because that would just make that work. So let's go back into buffer and actually just add that in. So buffer element, we'll make a little, probably some kind of get component count thing here, right? We can probably, I'm not sure what the best way to do this would be. I guess, I don't think it's going to be called often enough for us to cache that and ruin the kind of, just store that in memory. That'll be annoying. So maybe we can just say get element count. And then we can maybe just do some kind of switch here. Just thinking about this. Yeah, it's probably fine. If we just we'll add const here, and then we'll switch on the type here. And we'll say that if we have a shader type float 3, we'll just return 3, okay? And that is the component count. We'll return 0 here and assert saying that we have an unknown type. Again, this shouldn't really happen ever, but it might. And I guess because I'm a good person, even though I said I probably wouldn't, we'll fill out the rest of these. So we'll start with float, then we'll have float 2, 3, 4, then int, Oops. 2, 3, 4. What else do we have? Oh, mat 4 and stuff. Okay, sure. We probably don't need mat 4 and mat 3 to be completely honest with you. Because since when are these going to be... Well, I don't know. This is the component count though. It's not going to be used just for attributes. So we might need that. And then over here, I guess we'll have bool. So that's obviously 1. That's 4. That's 3. That's 2. That's 1. A mat 4 is going to be 4 times 4. Mat 3 is going to be 3 times 3. Float 4 is going to be 4, 2, 1. All right, that looks pretty good to me. Let's just tab this across and let's kind of try and align this somewhat just so that it looks nice. And there we go. Okay, cool. So there we go. Now we've got the element count. Sorry, not element count. This is get component count. Okay, so this is just how many components essentially we have here. Now, unfortunately, we also need, so we've got the component count, but we also need the actual OpenGL type. And this is like the base type. We can't have like vec3, we need specifically float. So we also need something that figures that out. Now, I don't really, like the type that we actually have obviously is inside our element, and it is like our, like, you know, we have like element type essentially. That's our shader data type. So what I'm gonna do is write a function up here that's obviously not gonna live here forever. That's gonna be called, we'll have it return a GL enum, which is what that type, I guess, what the Vertex attribute pointer parameter actually expects the type to be. And we'll say shader data type to OpenGL base type. Okay, so there's going to be a conversion between the shader data type to the OpenGL base type. So again, we'll have a switch statement on type. Oh my gosh, did that for me. That's pretty cool. Might actually have to do all of it now. I wasn't planning to. This is the one time I was planning on not actually doing all of these, but I guess I will have to now. So in this case, you know, we're going to just return GL float. And that's actually going to be the case, I think, for a lot of these. So this included, right? And you won't always need this function, but you do sometimes need it. And I guess for that it's fine. So this is int. And we haven't dealt with unsigned ints, but you know, if we really want that in the future, then we can just do that in the future. Okay, I don't even know. We'll just have bool, I guess. I don't really know because this isn't something that we do all day. So unknown that, and we'll return 0. Okay, cool. So there we go. So now what we can do is actually go over here and say that we have shader data type to OpenGL base type, and that's how we get our GL float. Now, whether or not it's normalized, again, really easy to do. Element.normalized. Oh my gosh, I forgot about normalization, didn't I? Normalized. So if that's true, then we'll do GL true. I knew I forgot something. Otherwise, GL false. Okay, the stride obviously is going to be layout, not element, but layout. Stride, or get stride. I thought I did that, apparently not. And then the offset is going to be element.offset, okay? And we'll cast this to a const void pointer. All right, bit hard to see because it's pretty big, but there we have our huge line of code, which I probably should break into multiple lines. I guess I will break it up into multiple lines just so you guys can see all of it. So we'll kind of have all of this stuff, I guess every parameter on a separate line, just like that, okay? And normalized, so we need to add that. So buffer, bool normalized, which again, like, I don't know, we'll just have it as false by default and no real way to set it for now. But we might have a constructor. I mean, look, let's just be nice. Let's just say bool, well, I'm not actually sure if this will work with initializer lists, but if we just do that, does that work? Yeah, that still works. Cool. So we can now optionally specify whether or not this is normalized. So normalization is good for if you're supplying like an unsigned int essentially, and you want it to automatically convert it into a vec4 of like floats. It can actually do that. You just say that you're supplying an int and that it needs to be normalized, and you'll get that. This has no member called getStride. Yeah, so what you can do now is if something were to be normalized, you could just do that, right? And again, not sure, yeah, so you wouldn't do that here, but if you had like a color as an unsigned int, we might actually try that out, you know? Why not? I'm feeling a bit adventurous today, and I'm feeling like actually doing stuff, even though this video is dragging on. Anyway, I'll stop talking. So getStride, we need to add that. So we have stride, inline, uint32t, getStride, const, return mstride. All right, I think that's it. Like if I hit F5 now, it should probably work. Let's just try. I mean, we haven't set the layout. That's we don't have to, technically speaking, because we're just reading it from here. Anyway, we have a compile error. Okay, no default constructors. That's a good point. So we need to add default constructors for all of these, right? Buffer element, because they need to be initialized, and buffer layout. Now, you could be less lazy with this and actually give your things default parameters. It works for here, doesn't work for here. Not gonna bother for now. Okay, let's hit F5 and see what happens. Okay, look at that, we have our triangle. How cool is that? That's really cool. We had that last time as well. Let's try and actually add a color now. So what I'm gonna do is inside my layout, just add a new float for. It's going to be my color. And then I'm gonna go into the shader and add layout location equals 1 in vec4 color, okay? I'm not going to use it for now. Let's just see if this even works, right? In fact, I don't even have to add it here. Let's just keep that out for now. I might just take it out at the end so I can undo it. But everything should work here. The only thing we need is actually everything here. So let's specify a color. Let's just make this thing pink, I guess. So we'll say 1, 0, 1, 1, right? That's kind of pink, magenta. So every vertex will be that color, and then we can probably interpolate between them in a minute as well, just to see what that looks like. But for now, we'll start with pink, which means we now have, I guess, 7 elements per vertex. Everything should be calculated automatically though. That's the beauty of this. And if we take away this, we should just get exactly the same result as last time, even though our vertex buffer has more stuff in it. Hopefully everything else did not need changing. Look at that, we still get our triangle, even though our vertex buffer is different. Clearly the stride and the offsets are working correctly. Otherwise it wouldn't, you know, it would read the next 3 vertices as being this, and our triangle would look different. Let's bring back the color and actually set the color inside. Okay, so we need to give this to the fragment shader. So we'll say out vec4 v color. Copy that, paste that here, call it in vec4 v color, and then we're going to set color equals v color. Okay, I'll just do that over here right after this one to override it. F5. Okay, so we get a black triangle, which isn't right. That's because I forgot to actually set the color. Awkward, right? You guys probably thought that my awesome buffer like layout code just wasn't right, but that's not actually it. It is actually in fact working because I wrote it, so you know. All right, there we have a pink triangle, pretty cool. Last thing I'll do is actually just change the color, right? So the color of this vertex I'll leave as pink. The color of this vertex I will set to like blue or something, so I'll get rid of this. And these are very harsh colors, obviously. I'm not trying to be like an artist in this case. And then I guess we'll set maybe one of them to like yellow or something. Let's hit F5 and see what happens. Okay, so now we have actually defined vertex colors. We have pink, yellow and green, blue. Before I can't honestly I can't commit this code because it just looks like absolute trash. So what I'll do is I'll make it just look nicer. So we'll say 0.8 and 0.2 just so that we're not kind of going all the way. Actually this needs to be 0.8. So we'll say 0.8. I'm just scaling the colors down a little bit so they're not as harsh because like honestly like and adding a bit more of other colors in because otherwise like it just as you saw just looks so bad. I really kind of hate it. This will make it look a lot nicer. So let's just hit F5 and see what happens. I need to get that printed on a t-shirt because apparently it's my favorite catchphrase ever. Okay, beautiful. There we have our triangle with all the vertex colors working. All of this stuff is now, you know, the layouts are all working correctly. Obviously what we actually needed to do is call this set layout, okay? And I guess what we can do just to be really cool is just to make sure that works, is just to make sure that we kind of get the layout from the vertex buffer. This is not gonna work because it's const apparently, and we don't allow constness. That's fun. We definitely should. We need a const iterator to make that happen, which I don't know. I thought that that would kind of just work, but I guess not. So I guess we need to also return a const iterator, which is, you know, fun. Const. Yeah, I guess that should work. Okay, done. And I'll actually put that in here just to make sure that we can't even access that layout thing. So this actually gets destroyed in this case after we've set it. So now it should be stored in the other thing. And I guess that obviously you probably brings that into a variable before putting it here, but for fun, I'll just leave it here. Let's hit F5 and see what happens. Yep, that's it. That's my phrase. Everything works, beautiful. And then finally, just to clean it up and make it super nice, I'll just do const auto reference layout equals that, and I'll just pop this in here and just check that code. And then now it's like ready to commit, and it will look nice. Okay, that's it. So that is buffer layouts. This is very powerful, what I've just written, right? Like this stuff is really nice. It's really satisfying to have a system like this in your engine, because that way you can just be really nice and descriptive. You can see that you can visually see the layout, right? I look over here, what do I see? You know, vec3 a position, vec4 a color. You know, float3 a position, float4 a color. Everything's here in exactly the same way that it appears here, which is just amazing, right? That's the kind of stuff you want. You don't want to be doing like fiddling with numbers, working out strides, doing all that stuff yourself. No, you describe your data in this way. It's going to be acceptable for DirectX. It's going to be acceptable for OpenGL. Everything's going to work. It's going to be beautiful. And you know, if you make a mistake like this, you know, look, clearly it's different, right? And that will, you can see kind of how that works. So this is kind of the idea of what I was kind of getting at with nice, elegant code, kind of like that English essay. Hopefully that makes sense. And I hope that you guys can learn something from this. Now, next time, again, I do want to move this into vertex array, and then this actual stuff, this actual like figuring out these vertex and trip pointers, that will be in the OpenGL vertex array, like, you know, class. So that'll be all kind of done through there. Anyway, I hope you guys enjoyed this video. If you did, you can hit the like button. You can help support the series by going over to patreon.com/thecherno. Please help support this series if you liked that episode, because all the support from all those people is what makes this kind of stuff possible. Now, if you do want to kind of skip ahead and see what I've written, and you know, I've got like a full PBR renderer, I've shown it off a few times, probably will make a video like specifically showing it off sometime this week maybe. But if you want access to that source code just right now today, you can just go ahead and go to patreon.com/thecherno, help support the series, and you will get access to that. Now, let me know what you thought of this whole kind of buffer layout. I quite like this way of dealing with it. I probably wouldn't even, like, I don't know, I feel like there's probably no better way to kind of do this unless you actually maybe, like, I don't know, it's be weird. What you could do is obviously parse the shader and then just figure out what it is, because in DirectX they're linked anyway. But if you parse the shader and you just kind of figure out what your attributes actually are, and then you automatically set and validate the buffer layout like that, maybe that would be even more robust, because that way there'd be zero code duplication and the layout would be actually automatically figured out from the shader. But aside from doing stuff like this, which I don't feel like that's necessary, to be honest, you get this stuff right and you can have a vertex buffer and your shader kind of laid out correctly, and everything should just work. So let me know what you thought in the comment section below. Hopefully I taught you guys something new and you kind of are now able to just write more elegant code. That's my hope. But anyway, next time, as I said, vertex arrays, we want to kind of get on with that and actually move some of this code that we've written here today in the application class into vertex arrays. As you can see, it's dark outside because that's how long this episode's been going for. I will see you next time. Goodbye.